Hello everyone. In this AV we would be talking about the remaining topics from the chapter of behavior of perfect gas and the kinetic theory of gases. So to start with, we will derive a relation between the temperature and the root mean square speed of the gas molecule. We know that the equation for pressure of the gas is given as pressure is equal to 1/3 m into n upon v multiplied by the square of the root mean square speed of the gas molecule. Now using this equation, if we rearrange the terms and we multiply v with p, then the equation becomes PV is equal to 1/3 m n v square bar. But here if you look at this equation, then m multiplied by n, that is the mass of one molecule multiplied by the number of molecules in 1 mole of gas, that is the Avogadro's number. If we multiply these two, then what we get is the molecular weight, that is m of the gas. So using this in the equation, we have the equation becomes PV is equal to 1/3 m into n is nothing but the molecular weight multiplied by v square. So this is my equation. Now we know that for 1 mole of a gas, the ideal gas equation is PV equal to RT. So we can use it in this equation. So in place of PV, I can also write that RT is equal to 1/3 m v bar square. Now from here I can find out the value of v bar square or v square. So if I have to find out the value of v square, then that would be, all the terms will go this side. So 3 will be multiplied with RT divided by m. Since this is the value of v square, we will have to take the square root. So if we take the square root, the equation looks something like this: 3RT upon m. Square root of v square will be, this is v root mean square speed is equal to root over 3r upon m, and let us write root t separately. Why? Because 3 is a constant, r is the universal gas constant, m is the molecular weight. So all these three terms are constant. So from here I can modify the equation as V RMS is directly proportional to square root of the temperature. This is how the temperature is related with root mean square speed of the gas. That is, the root mean square speed of the molecules of a gas is directly proportional to the square root of absolute temperature of the gas. So this means that faster the motion of the molecules of the gas, higher will be the temperature of the gas, and this is also known as the kinetic interpretation of temperature. Now we will see how temperature is related with molecular kinetic energy. So what we assume is, let the mass of 1 mole of the gas be m, that is capital M, and the mean square speed of its molecule be v bar square. So kinetic energy is given as half m v square. So this is equal to, if I substitute the value of v square, then the equation becomes half m. Instead of v bar square, we can take this equation, that is 3RT by m. So instead of v square we are writing 3RT by m. After substituting this value, now we know that the average kinetic energy of 1 mole of gas is 3 by 2 RT. 3 by 2 RT. Now, if there are n molecules in 1 mole of gas, so average kinetic energy for 1 mole or 1 mole of gas will be equal to this divided by the number of gas molecules present in 1 mole, that is this divided by the Avogadro's number. So we have 3 by 2 RT divided by n, that is Avogadro's number. So this equation will be 3 by 2, we rearrange the terms and we write R by n into T. Why do we write R by n? Because previously we have seen that R is a constant, that is universal gas constant, and n is another constant, that is Avogadro's constant, and the ratio of these two constant is a third constant K, that is the Boltzmann constant. So here when we have R upon n, we will substitute the Boltzmann constant here. So 3 by 2 kT. This is the average kinetic energy of 1 molecule. So what it means is different gases at the same temperature have the same average kinetic energy per molecule, and this energy is directly proportional to the absolute temperature of the gas. Now we come to degree of freedom and law of equipartition of energy. Now degree of freedom basically indicates the number of independent motion that a particle can have, or the number of independent methods of exchanging energy. We also say that it is the number of directions it can move, or how many coordinates will be required to specify its position or orientation, and that will be the same as the number of motion it can make. So degree of freedom we define as the number of independent motion that a particle or a gas molecule can make, or how many coordinates will be required to specify its position, or the independent method of exchanging energy. Now, to understand this, let's first take the example of a monoatomic molecule. We know that monoatomic molecule means it has only one atom. Now, when it has got only one atom, it's free to move in x-axis. It is also free to move along y-axis, so it can have this motion, and it is also free to move along z-axis. So here we say that For a monoatomic molecule, the degree of freedom is 3. That is x-axis, y-axis and along z-axis. So for monoatomic, the degree of freedom is 3. Similarly, if we have a diatomic molecule, then for diatomic molecule we have 2 atoms or 2 particles. In this case, it's free to move along y, along this direction also. But to move along the x-axis, this molecule will have to come along. So there is a restriction because these two are connected. Similarly, for this molecule, it can have the movement along y-axis and along z-axis. But if it wants to move along x-axis, then this molecule has to come along. So this is restricted along x-axis. If they move, they have to move together. So in this case, here the degree of freedom would be 1, 2, 3, 4 and 5. So for diatomic, the degree of freedom is 5. Similarly, if we talk about a triatomic molecule where the particle is of this configuration, which is a non-linear configuration, then here the restrictions are 3 restrictions are there. For degree of freedom, we can also use the formula D is equal to 3n minus r. So degree of freedom is equal to 3 into the number of molecules minus the restrictions or independent relation. So we know that for a monoatomic molecule or monoatomic particle, the degree of freedom is 3. So if we talk about for triatomic and non-linear, then it is using this formula. This particle, if we consider it as a monoatomic, then it could have 3. This also could have 3 degree of freedom, and this could have also 3 degree of freedom. So that means it should have 3 plus 3 6 plus 3 9, and minus it has got 3 restrictions. So 9 minus 3, it has got degree of freedom as 6. Or if we want to calculate it using this formula, then what we can do is 3 multiplied by n means number of molecules. So we have 1, 2 and 3. So 3 number of molecules minus r is the independent relation. So it has got 1, 2 and 3 independent relation. So that is again 9 minus 3, that is equal to 6. So for triatomic non-linear, the degree of freedom is 6. And for triatomic, so for triatomic linear molecule, we will have, linear means this structure. So here, if we use the formula D equal to 3n minus r, then degree of freedom will be 3 into number of molecules are 3 minus the independent relation or the restrictions. So we have 1 and 2. So minus 2. So 3 into 3 is 9, minus 2 is 7. So for triatomic linear molecule, the degree of freedom is 7. Now the example for monoatomic molecules would be helium, neon, argon. They will all have 3 degrees of freedom. Then for diatomic it would be nitrogen, oxygen, that is N2O2, or hydrogen. They will all have 5 degrees of freedom. For triatomic non-linear, that is the molecule like water, it will have 6 degrees of freedom. And if we talk about the triatomic linear, then the degree of freedom would be 7. The example would be like CO2. So now we will see that how much energy is given for each degree of freedom. That comes from the law of equipartition of energy, which states that the average kinetic energy per particle associated with each degree of freedom is half kT. This is the energy that is given for each degree of freedom. This is law of equipartition of energy. So for 1 degree of freedom, if the energy is half kT, then for monoatomic gas, where they have 3 degrees of freedom, the energy associated for monoatomic particle or monoatomic gas would be, the degree of freedom is 3, and for 1 degree of freedom the energy is half kT. So for monoatomic the energy would be 3/2 kT. Similarly, energy for diatomic would be, the degree of freedom is 5 and 1 degree of freedom has got energy half kT. So the total energy would be 5 kT. Similarly, energy for triatomic non-linear is, there are 6 degrees of freedom, and for 1 degree of freedom we have half kT. So 6/2 kT, that is nothing but 3 kT. And energy associated with triatomic linear molecule is nothing but 7/2 kT. Now we know that R upon N is nothing but Boltzmann constant. So if I take N on the other side, then I have R is equal to Kn, where N is the number of molecules present in 1 mole of the gas. So this is for 1 molecule. If I have to convert it into 1 mole, then all these numbers will be multiplied by N. And N and K, if they are multiplied, then it becomes R from this equation. So for 1 mole of gas, the degree of freedom for monoatomic would be 3/2 RT. For diatomic it would be 5/2 RT. For triatomic non-linear it would be 3 RT, and for triatomic linear it would be 7/2 RT. This relation is for 1 mole of a gas. So in 1 mole the number of gas molecules are nothing but the Avogadro's constant. Now we will see the evaluation of molar specific heats, that is Cp and Cv, and their ratio for gases, that is the ratio of Cp upon Cv. So what we do is, we consider 1 mole of an ideal gas which has got the temperature T, and since it's 1 mole, so there will be n number of molecules in the gas, And since this is the ideal gas, there will be no intermolecular forces, no internal potential energy, and the energy is totally kinetic energy. Now we know that the average kinetic energy per molecule of the ideal gas is half FKT. Now what is F? F is the degree of freedom, because the energy associated with one molecule is half kT, and if we want to find it out for the molecule, then we have to multiply half kT with the degree of freedom. So here F is the degree of freedom. So the average kinetic energy per molecule of an ideal gas is half FKT. Now the internal energy for 1 mole of the ideal gas will be internal energy U is equal to this half FKT will be multiplied by the number of molecules of gas present in 1 mole, that is the Avogadro's number, that is capital N. So we know that N into Kb or N into K is R from this relation, because R by N is Boltzmann constant. So Boltzmann constant multiplied by N will be R. So here N into K is R, rest of the terms remain the same, that is half FRT. Now if we differentiate it, then du upon dt is equal to half FR, because when you differentiate t with respect to t, dt by dt, it becomes 1. So we have the equation du upon dt is equal to half FR. Now what we do is we assume that the gas is heated at a constant volume and the temperature changes to, or temperature rises to dt. There is a slight increase in the temperature. So the heat given dq will be equal to the molar specific heat at constant volume multiplied by the increase in temperature. And since the volume is constant, that means no external work would be done. Now from the first law of thermodynamics, we know that du is equal to dq minus dw. So there is no work done, so dw is 0, and the value of dq, we can substitute this cv into dt. So this equation, that is the equation for first law of thermodynamics, becomes du is equal to, instead of dq we are writing cv dt, and minus 0, so we are not writing anything. From here we can find out the value of cv. So cv is nothing but du upon dt. Now we have got the value of du upon dt or cv. So substituting this value of du upon dt here in this equation, so instead of du upon dt, what we can write? cv, that is molar specific heat at constant volume. So instead of here du upon dt, we are substituting cv is equal to half fr. Now this is the molar specific heat at a constant volume. Now for molar specific heat at constant pressure, we know that Cp is equal to Cv plus R. Why? Because the relation or the Mayer's relation was Cp minus Cv is equal to R. This we have discussed in the previous unit. So from here the value of Cp would be R plus Cv or Cv plus R. So we are using that equation here. Now we know the value of Cv. So instead of Cv, we are substituting this value half Fr. So the equation becomes Cp is equal to half Fr plus R. Now R can be taken common. So we have Cp is equal to F by 2 plus 1 multiplied by R. So we have found out the value of Cv. We have the value of Cp. Now we will just take the ratio. So once we take the ratio of the two specific heat is given as gamma, that is Cp upon Cv. So we know the value of Cp is F by 2 plus 1 multiplied by R divided by Cv is half Fr or F by 2 R. So when we calculated, and simplify, then we get gamma equal to 1 plus 2 by f. I'll just show it to you here. The equation is Cp upon Cv. So the value is f by 2 plus 1 multiplied by r and f by 2r. So here r and r can be cancelled. Then we will be left with f by 2 plus 1 by f by 2. So if we write this denominator separately with both of them, then we have f by 2 divided by f by 2 plus 1 by f by 2. So f by 2 and f by 2 will cancel out and we will have 1 plus, here the 2 will go up and f will be in the denominator. So the gamma or Cp upon Cv is equal to 1 plus 2 by f. This is what they have written here. Now this is the ratio of Cp upon Cv or gamma. So what we conceive from this relation is gamma will be less if the degree of freedom is more. That means gamma decreases with the increase in the number of degree of freedom. So gamma and degree of freedom, they are inversely related to each other. Now we know that the kinetic theory of gas tells us that all these molecules of the gas, they are moving in all the directions with different speeds, and when they are moving, they are frequently colliding with one another, and after every collision their direction and magnitude of their speed will change. So now the average distance traveled between two successive collisions is what is known as the mean free path. Mean free path. Now the expression for mean free path is given as, so mean free path is denoted as lambda, which we discussed that it is the average distance traveled by a molecule between two successive collisions. Now the expression for mean free path or lambda is 1 by root 2 pi n d square, where n is the number of molecules of the gas and d is the diameter of the molecules of the gas. Now this equation tells us that the mean free path, that is lambda, varies inversely with the density of the gas. So if density is more, mean free path would be less because there will be more number of collisions. If there are more particles, there will be more collisions. Now if we consider it for n molecules of the gas, that is for ideal gas, where the number of molecules are Avogadro's number. So we know the relation that PV is equal to NKT. Now from here we will try to put N in this equation. So the number of molecules of gas, that is small n, is nothing but the Avogadro's number divided by the volume of the gas, N upon V. So N upon V, from this equation PV is equal to NKT. What will be N upon V? If we find out, then N will be kept as it is and V is brought this side. So N upon V is equal to P remains as it is and KT go in the denominator. So N upon V is equal to P upon KT. So we have the value of N as P upon KT. So now if we substitute this value in the equation for lambda or the mean free path, so the equation is lambda is equal to 1 upon root 2 into pi n d square. So what we do is we substitute the value of n here, that is p upon kt. So the equation becomes 1 by root 2 pi d square, and in place of n we will be substituting p upon kt. So p upon kt. Now this kt will go up, so the equation will look like lambda is equal to kt upon root 2 pi d square p. So the mean free path of the molecules of a gas is directly proportional to its absolute temperature, and it is inversely proportional to the pressure. Mean free path is directly proportional to the temperature or the absolute temperature, and mean free path is inversely proportional to the pressure. These two relations we get from this equation. Now finally we have to know a little bit about Avogadro's number. Avogadro's number is the number of molecules that is present in 1 mole of a substance. Now what is that number? It is, the value of Avogadro's number is 6.0221 multiplied by 10 raised to the power 23 molecules. That means when we talk about 1 mole of a substance, that will contain 6.0221 into 10 raised to the power 23 molecules. Now why is Avogadro's number important? It is important to calculate the atomic mass of an element. Then we can also calculate the molecular mass of a compound using Avogadro's number, and finally we can also calculate the number of atoms in a given mass of an element. So these are the reasons why Avogadro's number is important. And what is Avogadro's number? It is the number of molecules present in 1 mole of a substance. And using Avogadro's number we can also define, like using the value, we can define 1 mole. So 1 mole of a substance can be defined as the mass of a substance which contains this much, that is 6.022 into 10 raised to the power 23 molecules. That's all in this AV. Thank you.